Acid-base extraction calculations. Up to this point, we have discussed acid-base extraction in qualitative terms. For example, we know that if we have an acidic compound in a mixture, we should use a basic aqueous solution to convert it into a salt and extract it. What we will discuss in this webcast is the quantitative aspects of an acid-base extraction. When you have a mixture and you are extracting a compound, just how much of that compound is transferred into the new layer? Previously, I mentioned the partition coefficient, K. I described it to you as a measure of how, at equilibrium, a compound will prefer one layer over another. Let's say when separating a mixture, I want to get as much of a particular compound out as possible. How much solvent should I use when doing so? To answer that question, I can use K. Remember that K is the ratio of the amount of compound in the organic layer over the amount of compound in the aqueous layer, where the amount of compound is measured in grams of compound over volume of solvent. If we take this and substitute it into K, we get this expression down below, which with some rearrangement produces this final expression here on the right side. Do not memorize this equation. If you need it, it will be provided for you. What this equation allows us to do is if I know K and 3 of these variables, I can solve for the 4th one. Let's have an example of that. Let's say I'm going to perform what is called a single extraction. I know that the partition coefficient for compound A between ether and water is 8.5. What I want to know is how much of A would be extracted, in other words, how much will be present in the organic layer from a solution that contains 10 grams of A and 100 milliliters of water, if I use 100 milliliters of my organic solvent. Let's look at this equation that we just discussed. I know K, because that's given to me by the question. I know the volume of aqueous solution, because that's given to me by the question. And I know the volume of organic solvent, because that is also given to me by the question. And what I want is the amount in the organic layer. But I can't solve for that yet, because I don't know the amount in the aqueous layer. Okay, so I'm missing information. Can I find that information somewhere? Yes, I can, because I also know that the total amount of compound has to equal the amount in the organic layer plus the amount in the aqueous layer. So if I do some rearrangement, the amount in the aqueous layer is the total amount of compound minus the amount in the organic layer. And it turns out that I know the total amount of compound A, because that's given to me by the question. So if I take this equation and plug it in for NaQ, I get this expression down below. I know K, I know N total, I know VAQ, I know VORG, and so I can solve for NORG. If I do some algebra and isolate NORG, all I need to do is plug in the various values to give me a value of 8.95 grams in the organic layer. Pretty simple. Key points in this example. 1 is recognizing what each of these variables mean. 2 was recognizing that I can replace NaQ with N total minus NORG, allowing me to use all of the information in this question to solve for NORG. Now let us consider the amount that we extracted. 8.95 grams is almost 90% of the material. But let's say almost 90% isn't good enough. What could I do to extract more material? One thing you could do is increase the amount of organic solvent you use. Hopefully it makes sense that by using more organic solvent, we would extract more material. But that becomes quite inefficient. Is there a better way to increase the amount of material I extract? The answer is yes, and what we can do is use multiple extractions. In this example, I am using 25 milliliters of my organic solvent ether, but I'm using 25 milliliters 4 times. This is the same total volume as I used in the previous example, only now I'm using it portion-wise. In this case, I will use this equation, where the amount in the aqueous layer is equal to the total amount of compound multiplied by a combination of the volumes of solvents and the partition coefficient raised to this letter R, where R is the number of extractions of equivalent volume, and this is important. This equation is only valid if the portions of solvent you use are all the same volume. Okay, well, let's look at what I have. I still know N total from the question. I know VAQ still, again, given to me by the question. I know K, given to me by the question. And I know the volume of the organic layer, also given to me by the question. And then finally, I know R, which is 4, again, given to me by the question. So all I do is plug in the appropriate values. To get a value of 0.105 grams. But we're not done. What is the question asking of us? What it wants to know is the mass of A that would be extracted. It wants to know the mass of A in the organic layer. What did we just solve for? We just solved for NaQ. What we want is N-org. But we know that N-org is equal to the total amount of compound minus the amount in the aqueous layer. So, if I take 10 grams of compound minus 0.105 grams, which we just solved for, we get a value 9.895 grams. Notice how this value is much higher than what we had just solved for on the previous example. Previously, we extracted just under 90% of compound A. Here, we extract almost 99% of compound A. What makes this so impressive is that we used the same volume of organic solvent. All we changed is how we used that volume. In the first example, we used it all at once. In this example, we used it portion-wise. The take-home message here is that multiple extractions always extract more compound than a single extraction of the same volume. One more thing before I continue. I've shown you 2 examples using 2 different equations. I can ask you to solve for any variable in those equations. Be able to use algebra to solve for any variable I ask for. This includes solving for R. To solve for R, you'll need to use some basic logarithmic rules. Make sure you review those rules, because you will be asked to solve for R at some point. That brings us to the end of this webcast. To recap, the partition coefficient of a compound is a measure of which solvent of a pair of solvents used in an extraction a compound prefers. When trying to extract a compound from a mixture, multiple extractions of equivalent volume are more efficient than a single extraction of the same total volume. You have seen several mathematical equations in this webcast. Do not memorize those equations, you will be provided them if you need them, but do be able to solve for any variable within those equations.